All right, let's dive into one of the most powerful, most fundamental rules in the entire universe. Seriously. It's a law that explains everything from why your coffee gets cold to why time itself seems to only move forward. We're going to unravel this cosmic one-way street. So let's start with a really simple question, something you've probably never even thought to ask. You make a hot cup of coffee, you put it on your desk, and you know what's going to happen? It's going to get cold. But have you ever seen a cold cup of coffee just decide to heat itself up? No way, of course not. So why? Why does that process only go in one direction?
And it's not just coffee. Think about it. You spray perfume and it spreads out. It never gathers itself back into the bottle. A gas will always expand to fill a space. It won't just squeeze itself back into a corner. Scientists call these spontaneous processes. They just happen. And the key thing here, they are totally irreversible. This is what we mean by the universe's one-way street. It's like an arrow of time that only points one way.
Okay, so to really get why this one-way street exists, we need to introduce the main character of this whole story. It's a concept called entropy. And trust me, it's the hidden rule that explains pretty much everything. So what on earth is entropy? Well, the simplest way to think about it is that it's just a measure of disorder, randomness. It's basically a scientific word for messiness. The messier and more chaotic something is, the higher its entropy. I love the Hindi word here, avyavastha, because it perfectly captures that idea of chaos and disorder. Let's make this super clear. On one hand, you've got something like a perfect crystal. All its molecules are locked into this beautiful, neat repeating pattern. That is super orderly, right? So it has very low entropy. Now, on the other hand, you have a gas. Its molecules are just zipping around, totally random, bouncing all over the place. That's pure chaos, very high entropy. And here's the big takeaway. Nature, for whatever reason, always prefers to move from order to disorder, from low entropy to high entropy. And that preference? It's not just a suggestion. Oh no, it is a law. It's called the Second Law of Thermodynamics, and it is the official rule book for how change happens in our universe.
And here is the law itself in all its glory. It says that for any process that happens on its own, like our coffee cooling down, the total entropy of the entire universe always goes up. Not just sometimes, not usually, always. It's an unbreakable cosmic rule. The universe is just destined to get messier and messier. Now, we can even write this as a simple equation. It just says that the total change in entropy, that's the delta S total, has to be a positive number. And that total change is made of two pieces. The change in the thing we're actually looking at, which we call the system, plus the change in everything else, which we call the surroundings. As long as you add those two up and get a positive number, that process is going to happen.
Okay, so this is where things get really cool, because this brings us to a bit of a puzzle. What happens if the thing we're looking at, our system, actually seems to get more orderly? Wouldn't that break the rule? Let's find out. Let's take a look at a super common reaction. Two messy, chaotic gases, hydrogen and oxygen, reacting to form nice, orderly liquid water. Now hold on a second. We're going from random, high-entropy gas molecules to a much more structured liquid. It really looks like we're creating order out of chaos. And you know what? If you do the math for just the water molecules, for our system, the entropy change is negative. It actually decreases. The system has, in fact, become more orderly.
So here's the paradox, right? The system's entropy went down. How in the world can this reaction be spontaneous? Doesn't this fly in the face of the second law we just talked about? It feels like we just found a major loophole.
But we didn't, because we forgot about the second part of the equation, the surroundings. You see, this reaction is what we call highly exothermic. It blasts out a ton of energy in the form of heat. And where does all that heat go? It goes into everything else around it, into the air, the container, into the surroundings. And what does all that heat do to the surroundings? Well, it makes all the molecules out there jiggle and fly around like crazy. It creates a massive amount of new disorder. In fact, it increases the entropy of the surroundings by a huge amount, over 1900 joules per Kelvin. So now let's put it all together and solve the puzzle. This is just brilliant. Our system, the water, became more orderly, which cost us about 327 entropy points. But
We paid for that by creating a whopping 1,919 points of disorder in the surroundings. And when you add them up, the grand total for the universe is a big positive number. The second law is safe. The reaction happens.
Now, you can probably imagine that trying to calculate the entropy change for the entire universe every single time is, well, basically impossible. So scientists came up with an incredibly clever shortcut. It's called Gibbs free energy. And what it does is it cleverly combines the change in heat and the change in the system's entropy all into one convenient number, delta G. And the rule is just beautifully simple. For a process to be spontaneous, that delta G just has to be a negative number. That's it. It already takes the surroundings into account for you.
So this just makes it all so much easier. You've got the hard way, where you have to worry about the entire universe. Or you've got the smart way, using Gibbs where you only have to look at your system. If delta G is negative, you know it's going to happen. It's a total game changer for chemists and physicists.
So let's just recap the big ideas here. We learned that everything in nature tends to move in one direction, towards more disorder, which we measure with entropy. The second law makes it official. The total entropy of the universe is always increasing. And we solved the puzzle. A system can get neater, but only if it makes the rest of the universe even messier. And finally, we saw how Gibbs free energy is the awesome shortcut scientists use to predict it all.
So I'll leave you with one last, kind of mind-bending thought. If the total messiness of the universe is always irreversibly increasing, what does that mean for the ultimate future? What happens when everything is as disordered as it can possibly be? Something to ponder. Thanks so much for joining me.